Slide 1. Today we delve into the glass substrate revolution, the reality of 2026. Once considered a pipe dream, glass substrates have now become an unavoidable industrial reality for investors in 2026. Why are tech giants like Intel, Samsung, and Nvidia forcing themselves to choose fragile glass over proven organic substrates? We will uncover the physical limitations behind this shift and the winner's structure dominated by Japanese companies from the depths of the supply chain. Slide 2. The war page, wall and limits of organic substrates. First, let's address the fundamental problem, war page. Traditional epoxy resin substrates have a tendency to warp, like potato chips when heated, with generative AI chips becoming massive, exceeding package sizes of 100 square millimeters. This war page is now fatal. The heat from the reflow process distorts the substrate, causing tens of thousands of connection terminals to detach. The only material capable of countering this is glass. Glass is rigid and heat-resistant, maintaining flatness, no matter how huge the chip is. This is not for performance enhancement, but a mandatory requirement for manufacturing. Slide 3, technical deep dive, TGV and LIDE. However, glass has a weakness: it is brittle. We must drill millions of microscopic holes called TGV through glass vias into this glass to conduct electricity. If you use a drill, it cracks. Enter the laser technology known as LIDE, laser-induced deep etching. By altering the glass properties and dissolving it with chemicals, holes are created at high speed without cracks. Whoever controls this technology controls glass substrate manufacturing. Equipment manufacturers like LPKF in Germany and Disco in Japan hold the keys to this critical process. Slide 4. Supply chain winners, the Japan fortress. As investors, you should focus on who dominates this technology. Our analysis reveals a surprising fact. The enabling technologies to realize glass substrates are extremely concentrated in Japanese companies. AGC making the special glass material, DNP, Nippon printing, etching microscopic circuits onto that glass, and Disco cutting it without breaking it. Even if the final product is made in Korea or the US, the core materials and equipment cannot exist without Japanese companies. Slide 5, manufacturing hub, the Korean bet. On the other hand, the players taking the risk to mass produce are the Koreans. SKC's subsidiary Absolix and Samsung Electromechanics have made massive capital investments to operate mass production factories ahead of the world. While struggling with low initial yields, they aim to capture giant customers, like AMD and Nvidia, to become the TSMC of glass substrates. The period from 2026 to 2028 will be the era of the yield war, competing to see who can mass-produce large panels without breakage. Slide 6. The loser's crisis for BT resin. Where there are winners, there are losers. Facing the greatest crisis are suppliers of BT resin, which has dominated the core material of high-end substrates until now. Companies like Mitsubishi Gas Chemical, glass substrate technology, as the name implies, replaces the resin core with glass. This means they are being physically eliminated from the most profitable cutting-edge market. Of course, they will remain in general consumer products like smartphones, but the risk of losing their growth driver is immense. Slide 7, the silicon interposer twilight. Another potential loser is the silicon interposer. This is the silicon base currently used in TSMC's CoWoS. Silicon is expensive and limited to a 300mm wafer size. In contrast, glass can be processed in large panels, exceeding 500mm, offering overwhelming potential for cost reduction. Towards 2030, this will become a threat that silicon wafer manufacturers cannot ignore. Slide 8, yield economics. Here, let me answer an investor's question. Why use glass substrates if they are 2 to 3 times more expensive than organic ones? The answer is total system yield. NVIDIA's GPUs cost tens of thousands of dollars apiece. If a mere few $100 substrate warps and causes this expensive chip to be scrapped, the loss is colossal. Even if you use a glass substrate costing thousands of dollars, if it saves the chip, it is cheap in total. This is the economic logic that justifies high-cost glass. Slide 9, the Trojan horse, optical computing. Finally, let's talk about the further future. A glass substrate is not just a rigid board. It is the entrance to optical computing, a Trojan horse, so to speak. Glass is transparent. This means we can create optical waveguides inside the substrate, allowing communication via light instead of electricity. In the world of CPO co-packaged optics, which overcomes the limits of copper wiring, glass becomes the ultimate platform. Slide 10. Conclusion: investing in choke points. In conclusion, the glass substrate revolution is not a temporary bubble, but a physical inevitability. Investors, do not be swayed by the buzzword glass substrate stocks. but identify the choke points of the supply chain. Japanese companies with irreplaceable materials, Korean manufacturers taking risks, and the risk of legacy technologies being replaced. In 2026, the industrial map will be reorganized as transparently and sharply as glass itself.